Hello. Um, Quick video on continuous random variables. Um, Earlier in the courses, we've looked at discrete random variables, and you remember the example where we were looking at the number of occupants in a car and what's the probability that there's three people sat in the car and the next car that comes around the corner. Yep, so that's our random selection of a variable with a probability distribution. And with continuous random variables, we're looking at very much the same sort of thing, except that our data is continuous rather than discrete. So, for example, classically, it's weights from a distribution or the length of a component that's um, been made, which are typically normally distributed, or it could be the time for a component to fail, which would be exponentially distributed. So I'm going to take you through and have a think about what we're going to, how we use these and how they work. Okay, so a continuous random variable is like a discrete random variable in that we're selecting individual items at random from a population. And the important thing is that that population has a specific probability distribution, a PDF. And it could be any shape. So here I've just put a shape of a PDF. And what are the important things about this PDF? Well, we've got a minimum value and a maximum value to our range. So it's over a range of values that our variable like weight could take. It's got a PDF. Here I've written as an f of x. It's a PDF, and of course PDFs must be positive. We can't have negative probabilities. Yeah, we couldn't have a curve that goes down below the line because that would be a negative probability. And finally, the area under the curve here, which is the total probability, must equal 1. How can we use these or in practice? Let me give you a bit of an example of how we construct a random variable, continuous random variable, and then find out about it. And it's a classic example that, and I'm going to think about component failure. So what happens to components? Well, we make them, they fail at some point, and this is typically the sort of failure rate isn't even. It's what people describe as the bathtub curve in engineering, and that's because components tend to fail right at the start because of some form of construction problem with it. It wasn't properly made, or they just wear out at the end of their lifetime. Yeah, so we tend to see the sort of bathtub where it looks like it's full of water, the red line. Yeah, with not many failures here in the middle, but quite a few at the ends. And in this case, I'm just going to try and construct one that might work for us, a distribution. So let's assume our lifetime, our design lifetime is t, and the shape we're looking at here, if we put a dotted line down the middle here, looks awfully like a parabola, doesn't it, with the centre at t over 2. So let's assume that that's roughly the shape. So our PDF, our function here, is proportionate, excuse me, to t minus our lifetime over 2. Yeah, that's give us our symmetry here squared. So there we have a probability distribution. Yeah. What we don't know, if it's proportionate, what we don't know is what, there's some sort of constant here, isn't there? What we don't know at this point is what the constant is. But we do know that the area under the curve must equal 1. So therefore, if we integrate the function we've just created over the range from its minimum value, which is 0 here, to its maximum value, which is t, that integral should equal 1. Yeah. So if I integrate the function there, well, the k is not a variable dependent on t, is it? So I can integrate the element with the t in, and I get t cubed over 12, and that's multiplied by k, and that must equal 1. That allows us to find k, doesn't it? So k must therefore be 12 over t cubed. So we've now got a PDF which we think roughly fits our circumstances. Yeah, there it is. That the PDF of t is 12 over t cubed times a bracket of t minus t over 2 squared. And once we've got our frequency, our probability distribution rather, our f of x, we can find the mean and the variance. So a bit like we did in discrete random variables, if you remember, we found the mean because that was the sum of our xip of xi, yeah? Each of them is all a weighted average, isn't it? Here, because it's continuous, well, we've got an integral, but it's doing basically the same thing there, isn't it? And if we want to know the variance, well, before we looked at the sum again of the x, we had our x minus our mean, xi minus our mean squared times our probability of xi, yeah? And so here we've got the equivalent integral, and as we saw before, we could split that integral up, couldn't we? Because we've got our x squared element here, and we could then expand the bracket and then take out the elements that were dependent on u or effectively on x bar, and we found that we had our integral of x squared fx, and we took away our mean squared, didn't we? So exactly the same thing works. Rather than just doing sums, we're now doing integrals, but they're basically the same process operates. There are three probably famous distributions, continuous random variables, that people use quite a lot. First one we've used an awful lot, of course, before, and that's the normal distribution, isn't it? So if we were looking at weights, we've got a continuous random variable here, and we've got a PDF for it there, f of z, and for a standard normal, we know that the expected value is 0 and the variance is 1. So that is a continuous random variable, isn't it? We're selecting a weight at random from within a population which is normally distributed. The next one that you see quite a lot is the uniform distribution. So that one's saying that in the range, in this case our range is going from A to B, that the probability of getting any value in that range is exactly the same, unchanging, it's constant, yeah? And therefore we know that the area under this curve must be 1, so the probability, the PDF, is a constant value, that if that's b minus a on the bottom, then the height of this must be equal to 1 over b minus a for the area to be 1. And we can easily see that our expected value is right down the middle here, a plus b over 2, but we can calculate using the formula, the integration formula that we had before, that the variance of this distribution is a 12th b minus a all squared. And another famous one here is our exponential distribution. This tends to be used on a time basis, where we've got time going from 0 to infinity, and we're using it for failures, time to failure, time to a bus to arrive, yeah? And there's a separate video on this. But again, this is the PDF for that function, which is our yellow graph there, and for that we can find out what our expected value is and our variance for that distribution are. So you'll quite often see these, but you can create any distribution that you want that suits your purpose, as long as we've got lots of independently randomly selected samples values. Okay, so finally here's my quick summary. A continuous random variable is something like weight or height or time, and it's a continuous variable with its own PDF, and you're selecting points from within it. So the PDF has to have a range, a minimum value and a max, and the value of the PDF at all times must be positive because we can't have a negative probability, and the area under the curve, the total probability, is going to equal 1. And the formula for finding the expected value is we just integrate the x value fx from the so that should say min to max, and we can find the variance by doing a similar thing with that integral, and then we're taking off our mean squared. So I hope that's of use.